So we're going to be talking about rewrites, Newton's laws, assumptions, force types, and unit conversions. So first is your engineering formatting. This is critical towards your grade. That's why I'm showing you this. A lot of professors demand that you use engineering paper and very neat formatting to solve your problems, both homework and tests. And quite frankly, if I would have skipped just this part, I would not even have passed half of my classes, let alone get an A. I wouldn't have even passed. So it's very important to do this right, and that's why this is the first slide. So let's start with your heading. Everyone's a little different about where things are organized, but most professors have things laid out in similar ways. So there's only so many things you can put on the top here. So we have a date, a name, official course name, so in this case engineering statics, or if you're at a technical school, technical statics, and then your course number. So let's just say like Mech 1300 or something. Then your homework number, chapter number, problem number, things like that, section number, etc., etc. That's all up there as well. And these things might not be in the same places all the time, but this in general is what you're gonna have up here. Except for in this corner, you're probably gonna have the page number. So if this is our only page, we're gonna put 1 of 1. If this was our third page out of 5, we'd put 3 of 5. 7 out of 10, we'd put 7 of 10, blah blah blah, etc. Pretty simple, pretty straightforward. So this is Tom, the engineers. He did a pretty good job. He's pretty neat, obviously, filling this out. So he's got his date, he's got the course name, he's got everything specified, and he's doing good so far. So I hopefully can keep it up here. Then we have our restatement. This is literally just copying down what the question asks. This is all it is. That's all it is. So in this case, determine the product of inertia for the cross-sectional area with respect to the x and y axis. That's all it is. So if it was like determine this force times this force, then that's what you'll put. It's pretty simple. That's a no-brainer. That's not always demanded because it's so simple and so repetitive and so redundant, but some professors demand it, so I decided to include it. Then you have your diagram. I like to do this next because while you're copying things down with your restatement, why not just keep copying things down with your diagram? So that's unfortunately in real life you don't have the privilege of copying and pasting it off a Google search like I did in this scenario, but you want to make your diagram very neat and orderly, kind of like this one here. So you're going to want a straight edge. In this scenario, I would recommend straight edge for definitely the y and x axis, or if it's a 3D z axis as well. And for the lines here surrounding the shape itself, also the dimensions would be a great place to use it. And that's pretty much it. You don't have to get too crazy, and you don't have to copy down the diagram exactly. For instance, if I was to copy this down, I would not copy down this whole back part. It's not even important to the problem, and it's just not even important. It just adds a whole nother level of, unnecessary work. Unless your professor is very uptight, then maybe you should. And then we have our givens. So this was a poor problem to demonstrate givens because typically your givens come from your restatement, okay? But as you can see, there's very little to pull out of this except for what we need to find. So for our givens here, I pulled these out of the diagram, and we can see that we have multiple dimensions, which if you look, we have multiple. It's an understatement. We have every dimension, and it's a 3D object. We can see that as well. Although it's not very important to the question, it is still a given, and we can see that it is a given. And then our finds, in this case only one find, which is the moment of inertia around the x and the y axes. And you can judge what you need to find based on the chapter you're on. Once you get familiar with the chapter, it's not very hard. Then your assumptions. So we can assume our origins at C, this guy, because things are identical on both sides. You can see it pretty apparently. And then we can also assume it's static and that it's a rigid body. And this means that it's not going to move, and that it's not going to bend or fray or break. And we're going to get to that a little later in our course assumptions towards the end of this lecture. But yes, those are going to be on almost all of your assumptions for almost all of your statics problems. Then your plan of action, plan of attack, your plan. This isn't always done. Some professors do this, some don't. But basically, you're just going to go step by step, find each shape's area, multiply each shape's area with the distance between the shapes, blah, 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 blah. You're just going to do 1, 2, 3, 4, the step-by-step process of what you're going to do to solve this problem. I do this, and professors encourage you to do this beforehand. I do this after because I'm kind of a do it and then think about what you did kind of guy, not a think about what you do and then do. I'm not good like that, but I mean, if this helps, if it helps you to put out what you're going to do before you do it instead of doing it and then do this, then you can do that. But just know I do the solution first and I go back to this and fill this out later. I leave a big blank space on my homework and then just put the solution after it and then start on the solution. But you can do it either way. Obviously, you're supposed to do that first, and often professors won't even demand this. So, and finally, your solution. Obviously, this is not the real solution to this problem because it has nothing to do with the problem, because I wasn't going to do this entire problem out just to demonstrate this. So basically, for your solution, you're going to want all of your numbers down this nice orderly line. So each line, like, it's going to start right here, all of them are going to start right here, you know what I mean? It's going to be organized, and you're going to want to put your equation before you plug it in, like with the numbers, and then plug in for the numbers, and then solve, and then put your solution below. That's how it should go. And you'd always want to box your answer. If you have multiple answers, then you're boxing multiple things. It's pretty straightforward. I just wanted to really drive the point home here and why this is important and how it can help you solve the problem. Look, now you know exactly what you have. You know exactly what you need to find, wherever that is. Here it is. You have the graph right in front of you, so now you don't even need to look at your computer or your textbook or whatever. You have it all here now. You have all the information out of the problem, derived and simplified. So that's the real point of that. It can help. It depends on the person, but enough of that. On to the next thing. Newton's 3 laws of motion. So for the first law, every object will remain at rest or in uniform motion unless an external force causes a change in state. So let's take that in for a second. So let's say you're just sitting down in your chair right now, okay, and your friend beside you decides it's totally cool to push you, and he does. Well, that's going to cause an external force, and you're going to go flying out of your chair, or you're at least going to feel the force from him, and you're no longer going to be in rest. You're not going to be at rest anymore. You are going to be in motion from that external force. Yes, second law, F equals ma. The greater an object's mass, the lower the amount of force required to produce an acceleration opposed to a lighter mass. So, for instance, if I was to have a bowling ball and a volleyball, okay, they're the same volume. One is probably 20 times the mass, if not 50 to 100 times the mass of the other, the bowling ball, obviously. If these are both thrown with the same acceleration, but they have different masses, they're both going to exert different forces. The bowling ball obviously is going to exert a much higher force, and that's where this equation comes from, is this statement right here. Heavier things require less acceleration to produce an equal force from a lighter thing at a much higher acceleration. That's basically what this law states. So for every action, the third one here, for every action, there's an equal and opposite reaction. That person who pushes you, he's going to feel some of that force back. It's just how it goes. So Newton's first law. We've got our smiley guy. He's just doing what smiley guys do. They just sit there. He's having a good time out in the field. He's got a big red nose. Look at that. Look at those nostrils. This guy. He's a player. So anyway, he looks like he has no forces acting on him. And that is just not true, okay? He's got both his weight due to gravity, his F equals mg, mass times the acceleration due to gravity, which is 9.81, always, because we're on Earth and that's what it is. And then he's got the normal force, which is the exact weight of his mg, just in the opposite direction. And this is actually a good example of the Newton's third law. Every action has an equal and opposite reaction, because clearly these are equal and opposite. The exact same force that he's exerting down is coming right back up, right on him. So that's a good example of third law, but we're not focusing on that. So let's continue along the first law. So he was at rest, right? He was in a state of static equilibrium. All of his forces balanced out. Now his forces are about to get a little wonky, because his big bro comes along, this big red fella. He hits him right in the look at this, right in the temple. Can you see that? This is so unfair. And he sends him, he's gonna send him flying. Look at this force. This is insane. Nobody's seen a force like this before. So it hits him right in the side of the head here. This external force, okay? Now his internal force, obviously he had those, his X and Y's are still balanced, or his Y's are still balancing out, excuse me. But now look, his X's definitely don't balance out. The only thing over here that could ever stop him is a force due to friction, which is going to stop him, but not immediately. He's gonna go flying, he's tumbling. His static equilibrium is out of whack. External forces were applied, and now he's moving. This is a good example of what isn't going to happen in statics. In statics, there is always going to be an opposing equal force. It might not just be this, but it might be a force here as well. And both of these together might balance out that. And by might, I mean always in statics. That's always going to happen. Everything is going to balance. There's not going to be movement. This is not dynamics. But this is Newton's first law. External force, cause motion. He was in equilibrium. And now he's not happy anymore. He's smiling. He's frowning. Do you see that? That is a frown. So now our friend, he's pretty mad. So he wants to get revenge on the big guy, his big bro. We know our little guy has a mass of 2 kilograms. And our big guy has a mass of 5 kilograms. He hit the little guy with an acceleration of 4 meters per second squared. And if you use F equals ma, the equation, if you multiply 5 and 4, you get the force of 20 newtons. That is the force he exerted on our little bro. That's a big problem. Our little bro is going to have to go pretty fast to exert the same force, because that's what he wants to do. He wants to get revenge. So what does he have to do to exert the exact same force? Obviously he does. Do you see that picture? Do you see the arrow? I mean, that's massive. So if we just plug that in the equation, we know the force is 20. That's what the little bro has to exert. F equals ma. So F equals ma. So we have our force, which is 20, and we have our mass, which is 2 times acceleration. Excuse the lack of units. Divide by 2. And we get the acceleration has to be 10 meters per second squared. That's exactly what it is. And he goes flying, same speed. Now, how does this guy do that? We're going to find it out. But anyway, this is the second law, F equals ma. It just proves that a lighter guy needs to go faster to exert the same force as the bigger guy did, going much slower. That's basically what the law is there to do. So, Newton's third law. This is how he got his revenge. Our little dude, he's pretty smart. He's an engineer. He went to his little workshop and he crafted himself, as you can see here, I don't know how you couldn't, a rocket. He put that on his back, and now he's absolutely hauling. And that's how he's going 10 meters per second squared. And how does Newton's third law come in here? Well, this is how it comes in. Because we know he's going forward, right? I mean, that's what the rocket's doing. It's pushing him forward. But what if the rocket was in the front of him? It wouldn't be working. That's because the rocket is pushing this way. If the rocket was here, it would be pushing this way, which would cause this guy to go in the opposite direction. Therefore, we can confirm that the rocket is actually pushing a force that way. And would you look at this? Every action has an equal and opposite reaction. These are equal and opposite. Because the rocket shoots backwards, he goes forward. And these bigger arrows can demonstrate that, just like the crappy arrows I drew. But that's basically the point here. And that's the point with, pushing on the wall. It's going to exert the force right back at you. You can feel it. It's going to be in your joints, your elbows, and your shoulders. It's pretty obvious. You just don't pay attention to it. But it's always there. So then we come to Newton's law of gravitational attraction. It's not so known law because it's not so applicable to the real world. Essentially, this is an equation that takes into account the gravitational attraction between two particles. So typically this would be a planet and another planet, or like the planet and the sun. So let's just say the Earth and the sun. This is disregarded in statics because Earth's gravity is so much greater than any other objects on the planet. So when you're finding if something's statically determinate or not, you shouldn't be taking into account the gravitational of attraction of Jupiter on this truss. Okay, it makes no sense. It's stupid. Okay, I don't know why this is even in the textbook. I just know it's on a homework problem. That's why it's here. So basically, this is just for homework. This doesn't have too many applications in actual statics, and this is going to be the only time you see it. So here's the equation. F equals the gravitational constant g multiplied by the mass of the first particle times the mass of the second particle. So the gravitational constant, let's just say, multiplied by Earth's mass times the sun's mass, divided by the distance between them squared. And here you can see them all at the bottom. The force is always going to be newtons. The g is always going to be this number, 66.73 times 10 to the negative 12th meters cubed per kilograms per times second, or times second squared, excuse me. Your masses, you're always going to want kilograms. It's going to cancel out here. And you want meters because once again it's going to cancel out, and you need kilograms and meters. Make sure these are in kilograms and meters. So let's jump right into a problem with this question. So determine the gravitational force acting between two spheres that are touching each other. The mass of the first sphere is 250 kilograms and the second is 300 kilograms. The first sphere's radius is 300 millimeters and the second's is 500 millimeters. This is very similar to a homework problem from the textbook. So that's why I made this. It's very similar and it gives you good experience. So here's a picture. I actually drew a picture of it because I know the textbook didn't have any, and I thought it would be good to visualize this. So here's our first particle. These are really small, by the way. This would never happen. 250 kilograms in a 300 millimeter radius circle. That is absolutely insane. I don't know what this thing is made of. I have absolutely no idea, but this is totally theoretical. So we got our masses, we got our distances, and let's solve. So right now I can tell you we know M1, right? M1 is 250 kilograms. Says it right up there, it's a given. We also know M2, 300 kilograms. Again, that's another given right up here. And then we know G, 66.73, meters cubed per kilogram times second squared. So easy to remember that one. And then we have our R, and we don't know our R right now, but it's pretty easy to find out. Look, because we know the radii of these two, we see that this one's 300, and we see that this one is 500. And all you have to do is add those together. Just bring this around and look, it's 500, bring this 300, we'll get 800 millimeters. But this, excuse me, this has to be in meters, so we have to convert this. We know meters are a magnitude of 3 times larger than millimeters. So let's just take this down here. It's pretty simple. So to convert this to meters, we're going to go over with a decimal point. 1, 2, 3 times 0.8 meters. So then we're going to go up here, 0.8 meters. Then we just plug it into our equation. Plug and chug. So let's just put our equation down real quick. 2 over r squared. Then we'll plug in. So our force here equals 66.73 meters cubed over kilograms per second squared. I'm sick of saying that one. Multiplied by our masses, multiplied by each other, which is 250 times 300, all over our distance between the two particles, 0.8 meters. Plug and chug that in your calculator, and we're going to get a resultant force, and this is going to be small because gravity, as you can see, is only significant on a very large scale, just like we can see with the planets and all of that solar system stuff. So we're going to get that 7.82 nanonewtons, or micronewtons, excuse me. Put a box around that, and there you go. Yep, that's that. So now you know how to do that. Then we have our course assumptions. What is going to be assumed throughout this entire course right here. These are very important for understanding the basics. So all bodies in statics are static. How ironic. They are motionless. All the forces balance out like earlier, like I explained with our little ball guy. Each vector direction sums to 0. And watch this. Boom. Look at this. So each vector direction sums to 0. So on this guy, this is 2D. So we have our x direction. Hold on, let me draw. Oh no, I could have went better. So x and y. So we have our x forces like this guy, and we have our y forces like these guys, and they all balance out. Everything here has to come out as motionless. There can not be an x force and then no other x force, or an x force that's way larger than another one. Okay, they have to balance out with each other. That means this guy right here, this guy, okay, has to be equal to, since this guy's on an angle, he has both an x and a y component. This has to be equal to this. So if this one's 20 newtons, this y component of this resultant force here also has to be 20 newtons. If this is 30 newtons, and this is 10, this little guy, then this has to be 40 newtons. Everything has to balance out, and this is critical to solving problems. This is a very important concept to understand. All the x, y, and in 3D z components all have to balance each other out. There cannot be motion, or this is not statics anymore. This is a different class. Go on your way and find a different class. So then we have rigid body. That's our other one, as you saw earlier on the piece of engineering paper. All structures have infinitely resilient parts. There is no bending, breaking, cracking, etc. As you can see over here, our square must be made of some sort of insane material to withstand all these forces. But it does, and it doesn't bend at all. Can you believe that? It's because this is statics. So you see this guy right here? This could be made out of paper mache, and it's still going to hold up because this is statics class. Okay, it doesn't matter what this material is, it's infinitely resilient. This force is crushing it right in the middle of these two pieces, and it's still holding up. This is what statics is not. That is what statics is not. No, there is no bending or breaking. You will not see that in a problem. You shouldn't ever assume that. Okay, you shouldn't say like, oh, it's going to break the bridge anyway, it's not going to work. No, okay, it doesn't work like that. It's going to always be like this. Even if it's paper mache or styrofoam, it's always going to be like this, never like this. Never. Okay, we're assuming these materials are unlike anything we've ever seen. So there are two types of forces. There are external forces, as actually we just saw in the last PowerPoint slide. These forces act on the outside surface of structures. So let's say this is our little truss, this is our bridge, and there's a guy here because he loves this bridge. He goes here every day to walk his dog for some reason on this dangerous bridge. And this wind comes and it exerts external forces on this bridge. Okay, that's why bridges are built so tough and to withhold cars and trucks and blah blah blah. But basically, these triangles are all to counteract external forces, and I guess you would consider people and cars external forces as well. In fact, I don't guess, I know. So, two examples of external forces: wind, cars, and people. All blowing and standing and driving on this bridge, all coming from external areas. So the result, internal forces are results of externally applied loads on the internal members, joints, and base connections. So as you see down here, this is a roller, this is a pin. These will be introduced later on. But these are actually critical in statics because they exert forces counteracting the external forces, as you'll see right now. So in this scenario, you'll notice these are pushing against them. Actually, this arrow should be in the opposite direction. Should be right there, because these in the x direction are negative. Therefore, we need a positive one to cancel them out. So basically, these are examples of internal forces. Our roller only has a y force, and our pin has both an x and y force. Okay, and those are both going to exert back on the bridge to maintain that static equilibrium. No motion, no bending. And then this guy right here, actually, let's go over here. You see this? That's what this is. This is a joint, is what these are called. These are how the members are connected. This is a member. And if you don't get this right now, this will come later. These are later chapter things, but I just want to introduce you to them so you're not familiar later. But basically, yes, this joint is down there. And as you can see here, there's actually forces acting on it. These members are actually acting on this because they're absorbing all this load, which travels throughout these members into the joints. So here's our roller, vertical. That means our member has to be pointing down. Okay, this because it's the only y direction, therefore it has to balance out. And because this x force is going this way, this one has to go in the opposite direction to balance out. So it's as simple as that. There's internal and external forces that will be covered in extent later on. Okay, excuse me. Units worth familiarizing yourself with. So typical statics courses use both US customary units and metric units. Depending on where you are, you might just use metric. It's a lot better. US customary is absolutely just, it's frustrating. The categories for most units include the following: weights, kilograms and pounds, obviously pounds, geez. Distances, meters, inches, feet, centimeters. Forces, newtons, kips, tons and pounds. Moments, basically a rotation is what those are if you're totally unfamiliar. Basically a force times a distance, kip times a foot, force times a distance. That's what a moment is. And then moment of inertias, and those are going to be to the fourth power. Inches, centimeters, meters, millimeters, etc. Things like that, feet maybe. Those are much later. Those come much later in the chapters, much later. And then we have some review here. Occasionally in statics, units will have to be converted. They are mostly simple metric or imperial conversions that can easily be memorized. I was looking through the Hibbeler statics book, excuse me, and there were a ton of questions that were really hard conversions, and I don't understand. You really do not need that many it's really not necessary. It's pretty simple for the most part. I did include a couple more difficult ones in this PowerPoint, not very hard, but we will be going over the homework. But basically, it's not that complicated throughout the course. And some examples include practical examples that you're actually going to need to know. These are the basic ones you're going to need to know in this course. Dimensions given in both inches and feet. Okay, that's one example. So like dimensions are given in centimeters and millimeters. You have to convert either to centimeters or millimeters or inches to feet. This conversion here, obviously you can divide or multiply by 12, whatever way you want to go. And then another common one is weights given in kilograms, but they need to be in newtons because you need forces when you're exerting on things in this course. So basically, to convert kilograms to newtons, all you do is multiply by 9.81 meters per second squared, and that will give you a newton, because we're on Earth, like I stated on Newton's law not too long ago. Then the last one here is maybe a force is given in pounds and the other in newtons or something like that. You're gonna have to convert one, and that's not very common in real life. In fact, not at all really common, but who knows? This is all theoretical, so anything's possible. Conversions to remember: pounds to kilos. Okay, there are 2.205 pounds in 1 kilogram. That is important to remember. I know that off the top of my head. I encourage you just to sit down at night for 2 nights. Just 2 nights, 5 minutes, and just memorize what I have right here. And it will help you out so fast, so quickly. And not only statics, but all your courses. You need to know these conversions. They're so basic and simple. Another one is kilos to newtons. Like I said above, just multiply by 9.81 meters per second squared. And another one to remember is every third metric prefix. So let's say like you have a byte, like a byte of data. This is a very easy way to remember the higher metric prefixes. So everyone knows, all the new kids, okay, I say like I'm not one, but we all know that it goes byte, kilobyte, megabyte, gigabyte, terabyte, and then petabyte even. Those all go up by 3s in the actual metric prefix language. So a kilobyte is 10 to the third, a mega is 10 to the 6th, a giga is 10 to the 9, etc., etc. And those are all very important to know, at least the first 3 there. And then once we get smaller, a lot of people know centimeters. That's 10 to the negative 2. Millimeters is 10 to the negative 3. And then after that, we have micro, which is 10 to the negative 6. And then nano, which is 10 to the negative 9th. And those are all very important as well. Not only in statics, but all your courses, again. And now we're going to do some problems. Isn't that just a ton of fun? So this is one I've already said to you a million times. This is so easy. 4 kilograms. Okay, we're going to do the brackets because we're very neat here. 9.81 meters per second squared. And then you get a newton, because a newton is a kilogram multiplied by a meter per second squared. That's what a newton is. A force, or a mass times an acceleration. And from that, we get 39.24 newtons. We're going to box our answer. These are good habits we're developing here. Very good habits. I know I sound like your mom. Convert 145 miles per hour to kilometers per second. Okay, this one's a little bit harder, not too bad. But now we're actually going to use unit conversion language, if you will, call it that. I'll show you here. 145 miles. Okay, and then miles is over hour. 145 miles. Listen to how I say that. 145 miles per hour. Per hour. So 1 hour. There's only 1 hour here, and there's 145 miles. And we want to convert that to kilometers per second. So here we are. Let's first convert to hours. So how many seconds are in an hour? There's there's not 30 seconds in a minute. There's 60 seconds in a minute and 60 minutes in an hour. That means in 1 hour, we're going to have 3,600 seconds. 60 times 60, and there you go. And notice how I put hour on top here. That's because once you cross multiply all this crap at the end, once you multiply all this stuff across, okay, these hours are going to cancel out because one on top and one's on bottom. So when you convert these units, you always want to make sure, like if I was to put seconds on the top here and hours on the bottom, now I have hours squared and miles times seconds. Okay, that makes absolutely no sense. So you obviously want to cancel out these units every time, and you want to make sure they're opposite each other from top and bottom every time you make a conversion. I will show you more examples of that. So now we have miles per second, and we're halfway. The battle is halfway completed here. So here's another conversion I memorized that I encourage you to. In 1 mile, there are 1.61 kilometers. That's a very common one. You're going to see that a lot. And then our miles cancel. Would you look at that? So for an answer, we're going to get a very small number because this is in seconds. So we're going to get 0.065. Where'd my dot go? Kilometers per second. That was easy, right? That was pretty easy. That was not that hard. Now we're going to convert 20 pounds to kilograms. So this is another super easy one. So 20 pounds over 1. This is another good habit, okay? When you don't have a bottom unit like I did in the previous question up here, just put a 1 underneath. It's just a nice placeholder, and it's just a good habit to get into. I actually really encourage it. So then another good conversion that I preached to you before about was knowing pounds to kilos. So we know there's 2.205 pounds per 1 kilogram. How do you guys say it? Kilo or kilo? I think it's kilo is how you're actually supposed to pronounce it. That's what I was taught. I don't know though. I don't want to upset anyone. So that's going to equal 9.07 kilograms. That was elementary right there. And then if you can read this over all of our nasty text, actually hold on. I'll get rid of that. Erase. Okay, so now we got this is probably the toughest one we've seen. So 50 megagrams to tons. Now this is going to involve some micro conversions. I don't know what you want to call it. Some inter conversions to get to tons from megagrams, because I have no idea what the conversion to that is. So let's just take it piece by piece here. So we got 50 megagrams over 1 because we're getting in good habits. And that's going to be multiplied by, let's convert megagrams into kilograms because we know the conversion from kilograms to pounds. So, and we also know the conversion from megagrams to kilograms. So a kilogram is a magnitude of 3 less than a megagram. So from that we can tell that 1 megagram is going to equal 1,000 kilograms. Now we're making progress, and now our megagrams cancel out. So how many kilograms to pounds? We know 1 kilogram is going to give us 2.205 pounds. No way. We're getting very close already. Now our kilograms cancel. And now how many pounds are in a ton? That's something I know. It's somewhat common knowledge, but it's going to be 2,000 pounds. Let me put a comma here. Per 1 ton. That's going to give us an awesome answer of 55.12 tons. Wasn't that easy? That was not that hard. These are not that hard. Very simple. Our final two. Just want to drive the point across with a couple more here. 653 millimeters cubed over 1. Do I even have to say it because of good habits? And then I had to look this conversion up. This is the only one I had to look up here, and we know that from Google, we know that 1 inch is equal to 25.4 millimeters. So look at this now. If you think I'm done right now, you're absolutely insane, because these cancel and these cancel and make a 2. Now this is squared. We had 3 here, so this has to be repeated. You guessed it, 2 more times. So 1 inch over that again, that cancels. Then 1 more 1 inch. I don't know if I can spell it. 1 inch over 25.4 millimeters, and these all cancel. And then if you take a look here, inch times inch times inch is inch cubed. So then you just divide 653 by 25.4 3 times, and your answer is going to come out to be, you guessed it, a small number, because millimeters are very small. 0.0 398 inches cubed. It's gonna be hard to, there we go. Okay, gonna erase all this again. And now we're gonna convert kilopascals to atmospheres. Kilopascal is a unit of pressure. Don't know how familiar you are with that, but basically a unit of pressure is a Newton over an area. So a Newton over like meter squared, that's what a kilopascal is. A force over an area, really, is what it is. So let's take a look here. So 50.7 kPa, and Pascal is a very small unit, so typically you'll always see it in kilo, or kilo, my bad. So there you go with that. Okay, over 1, again, you should always do this. Look at this, I'm gonna add this. And I happen to know this conversion because I've taken thermodynamics, and I know that there are 101.3 kilopascals in 1 atmosphere. An atmosphere is basically a regular sized unit of pressure. Pascal is very small, because even 101 kilopascals is 1 atmosphere. A pascal is very small. So then you cross that out, and then this gives us a very neat answer of, guess what, 0.5 ATM. And that's all the unit conversions we're going to do today. Drop a like. Tell me what you liked about this. Comment, and the subscription would mean the world. So I really appreciate it. Thank you so much.